I believe we left off on Monday on number 13. So we'll go ahead and start there. And that actually leads us into chapter 3 stuff. Okay. Chapter 3 was all about exponential functions and logarithmic functions. So you'll notice here we have a good little exponential function using e, right? Using a base e. Percentage of doctors who prescribe a certain new medicine is P of t equals 100 times this little expression, 1 minus e to the negative 0.25 t, where t is time in months. So this one has a bunch of different parts, so I went ahead and answered it all wrong just so we could see all the parts. Part 1, P of 1, what is it asking you to do? Just plug in 1. And so part A is just simple calculation. You're just plugging in 1 and then plugging in 6, seeing what you get. P prime. That's taking my derivative. Okay. So how do we get this derivative here? Oopsies. So if here's my function. How can I take my derivative? If it might be a little confusing with that 100 out in front, so let's go ahead and distribute that 100. And now when I take my derivative, what's going to happen to that first term? Oh, this term will. I'm talking this term. If I take my derivative, it goes to 0. Right. Derivative of this term is just 0, so then I'm just focusing on this term. What's my derivative rule for these exponential functions? Oh goodness, that's supposed to be a p. I have a constant up there with my variable, right? I have a constant times t. What am I going to do with that constant if I take the derivative?
Bring it down.
Bring it down and multiply. Right. So I'm going to have negative 100 times negative 0.25. That just gives me positive 25 e to the negative 0.25 t. And with these exponential functions, you leave everything else the same, right? Everything else stays the same. E to the negative 0.25 t. There's my derivative. Awesome. Part C. This one you might need to read through it a couple times. How many months will it take for 90% of doctors to prescribe this new medication? Part B, we just calculated the derivative. Does this involve the derivative? It does not. I don't actually need the derivative for this at all. If I'm wondering how many months, what am I solving for? T. I'm solving for T. But it's asking how many months will it take for 90% of doctors. That's what this equation is all about. This equation is all about what percentage of doctors are actually using it, which means I don't have to use I'm not using the derivative at all. I'm just using my equation. So for part C, all I'm doing is just setting my equation, my original equation, equal to what? 90. Just set an equation equal to 90. Okay. Ooh, part D. What happens if I let t approach infinity? What's going to happen to my function? We can see my function right here. This is the function. What's going to happen to this function if I let t get infinitely large? Okay, is it going to go to infinity? Why not? Why will this converge instead of diverge? Why will this converge? What do we notice with this exponential function? It has a negative exponent. Because of that negative exponent, if I let t get infinitely large, what happens to this term? It goes to 0. Right. It's getting infinitely small because I have that negative exponent. Since that term's going to 0, if I take the limit as t approaches infinity of p of t, I just get 100. Makes sense, right? If I let time go on, eventually 100% of doctors are going to be using this medication. It's that good. whatever medication is. Awesome. That's what it says by discuss its meaning. Okay. Any questions about this one? Okay. Then let's move on. Number 14. Oh, there we go. Okay, so more exponential functions, but this is where we finally get into finance, present value, future value. Let's see, did I miss anybody else? Yep. Okay. Present value, future value. Remember, these type of functions, these type of questions really boil down to the function, right? Your principal, or the amount that you have, is equal to your initial value, e to the rate times t. Right? We've seen that equation so many times. Any situation like this where we're investing money, it's going to boil down to this equation. Right? It does specify that it's compounding continuously, which is why we use this equation for it. Okay. Where do I plug in the 10,000? Yeah, I want to have 10,000 by the end of this. So 10,000 represents your future value. So 10,000 goes over here. And then I'm solving for P naught. How much do I need to invest right now? Okay. This is what I'm solving for. And then, of course, R is your rate. So in my case, 0.041. And T is your time at the end of 5 years. Okay. Sorry, I know that's kind of hard to see. Okay, any questions about this one? Yeah, Tim.
0.41 be negative?
Great point. So Sam's asking, shouldn't that be negative? Well, that's because there's actually another way to do this. But if we put 10,000 over here, this is how we want to set it up, because we want it to grow. We want to start out with some amount that I don't know yet, and then we want that value to grow into 10,000. But we can set this up differently. Remember, we can also set this up like so. Right? If we just switch where the P naught and the P are, then we need a negative up in my exponent to make it work. Okay. So this is my alternate way. To calculate this. Okay. Other questions? Awesome. Okay. Next. Number 15. Let's talk number 15. A few different parts to this one. We have salvage value. Okay. This is just, part A is just taking the derivative of this function, 6,700 times 0.78 to the t. This is an exponential function. Why is it exponential? Because your variable is in the exponent. Okay. Please don't use your power rule formula for this. It will not work. Okay. So to take the derivative, I'm not using power rule, I'm using my exponential rules. Okay. How do I take the derivative if my base is not e? E to the t is a really easy derivative, right? The derivative of e to the t is just itself. But how do I do it when my derivatives, or when my base is not e? Yeah, you use the natural log. So the derivative is going to be very similar to where, when I take the derivative, am I going to keep this 0.78 to the t? Yeah, you're going to keep that. That's going to stay there as part of your derivative. Okay? Of course, the 6,700 is going to stay as well. But you're going to keep the 0.78 to the t, but then what do? multiply it by
Oh, the natural log.
the natural log of the base. So there's your derivative. Okay. Now, what does v prime actually mean? You're really looking for that wording, rate of change. A derivative is a rate of change. So that's what you're looking for here. In our case, it's part C, or option C. V prime of t is the rate of change of that salvage value t years after purchase. Questions about this one? Any questions? Okay. Okay. $17. So these are all still chapter 3 questions. Okay? Because we're still working with exponential functions. Here's a chapter 4 question. Chapter 4 is when we got into antiderivatives, right? Integrals and antiderivative. So let's see how this relates. A particle is released as part of an experiment. Its speed t seconds after release is given by this function. So it gives us a velocity function, where velocity is in meters per second, yada, yada, yada. How far does the particle travel during the first 4 seconds? How am I going to do this? What do you mean by plug and chug? What about plug into what? Oh, I do need the antiderivative. Because if I just plug in 4 to my velocity equation, that's going to tell me how fast I'm moving after 4 seconds, but not how far I've moved. So this goes back to what we talked about with antiderivatives, right? If your function is a rate function, then the antiderivative gives you the total change. The antiderivative or the integral of a rate function gives you total change, and that's what I'm looking for here. So I need the antiderivative of my velocity function. Do I have bounds?
Yes.
Absolutely. If I'm looking over the first 4 seconds, what are my bounds? 0 to 4. And then part B is very, very similar. So this is part A. Part B is very, very similar. This is not a negative sign. This is an arrow. Realizing that could be confusing. Part B, how do I change things? What's the only difference in part B? Change your bounds. 2?
8 and 4.
Yeah, in our case, it's the second 4 seconds, so it would be 4 to 8. Right? From 4 to 8, that represents the second period of 4 seconds. So for part B, you're going to do the same thing, but your bounds are just from 4 to 8. Okay. Okay. Moving on. Number 17. You'll notice with this review, there's only one chapter 4 problem. And now we're on to chapter 5. So, interesting. How convenient, since chapter 4 was the test that we really struggled on. Okay, chapter 5. So this is 5.1. What did we learn about in 5.1? You guys remember? Consumer surplus and producer surplus. And remember, 5.1 was the nice one where every single problem was the exact same, just different equations. Same thing here. Same exact type of problem. Find the equilibrium point, and then find your consumer surplus and your producer surplus. Okay. How do I find that equilibrium point? Set them equal to each other. Right. I'm just going to do x minus 8 squared equals x squared plus 4x plus 4. Okay. Do yourself a favor. Expand this. What is x minus 8 squared? That's just x squared minus 16x plus 64. And that'll make it a little bit easier to solve. Once you have that equilibrium point, calculate your consumer and surplus and producer surplus just using that formula sheet that you guys have. Any questions about this one? Any questions? Okay. Yeah, what's nice is we're getting into the stuff that we've done more recently. So you shouldn't be as confusing. Okay, number 18. This is from 5.2, but if we take a close look, let's see. In 18 years, Maggie Willow is to receive $100,000. Okay, if she's receiving that in 18 years, is that a future value or a present value? It's a future value, right? That's what she's going to get eventually. So it's not a P naught, it's a P. Okay? Under the terms of a trust established by her grandparents, assuming an interest rate of 5.3%, compounded continuously, what is the present value of Maggie's legacy? You'll notice 5.2 is where we talked about an accumulated income stream. Is that what I have going on here? No. This goes right back to that same formula that we've already talked about. P equals P naught e to the RT. What's P? 100,000, right? Because that's my future value. That's what I want it to end up equaling. What's R? What's my rate? In my case, it's 5.3%. What's T? In my case, it's 18 years, right? That's when the trust is going to mature. So T is 18, and I'm solving for P naught. So it's the same exact type of problem as 14. Same type of problem as 14. Let's get rid of that. Okay. What about number 19? At age 35, Ronald earns his MBA and accepts a position as a vice president of an asphalt company, yada, yada, yada. Assuming that he will retire at the age of 65, having received an annual salary of $105,000. Is this different? Yes. Now I have an accumulated income stream because I'm talking about an annual salary that he gets every single year. We okay with that? This is an income stream now, which means I'm going to use those income stream formulas that I have, right? A is equal to your income stream, right? R represents your income stream over your interest rate, lowercase r, e to the RT minus 1. Which one will this one calculate? This is future value, right? This is the one for future value. And then present value looks very similar, except you switch it around and you have a negative exponent. Okay? And very nice. You'll notice part A and B are just find the accumulated present value, find the accumulated future value. So you're just going to use both of these formulas here. Remember, in order to use these nice simple formulas, what are we assuming about my income stream? It's continuous. And it stays the same. Right, it's staying the same. What are we assuming about Ronald with his vice president position? He doesn't get a raise at all, right? So that's what we're assuming in order to make this a little bit simpler. Okay. Any questions about these type of problems? Any questions about these type of problems? What, in my case, what's my T? What time are we looking at? He's starting at age 35. He's retiring at age 65. 30 years, right? T is going to be 30. Okay, very nice. What's uppercase R? Right. Uppercase R is what he's actually earning each year. So in our case, $105,000. Okay. Number 20. Number 20. And this is a mix of the two. Okay? This is the problem where, let's see, Bob and Laura Dutch, what's a good grandparents' names? Have a new grandchild, William, They want to create a trust fund for him that will yield $200,000 on his 18th birthday. What do I already have? What do I already have? What information has been given to us?
Birthday?
We just got to listen to what I say, guys. So I haven't even gotten to A or B yet, but what do I have?
18 years.
18 years. I have time. I have the T value, so I know what my time value is. And what is the 200K?
Future value.
It's the future value. It's what I want to end up with. So I have the future value and I have the time. Let's look at part A. What lump sum would they have to deposit now at, there's your rate, 5.7%. Okay. Part A, am I using either of these for part A? No, because the whole idea of part A is let's not do a continuous income stream and just think about what would I have to invest right now in order for me to just let that sit for 18 years. Okay. So that one, part A, what are you using? You're using this again. Okay. Part B, now they're deciding to invest a constant income stream, right? A constant money stream of a certain amount of dollars per year, and you're solving for that. So in number 19, you were plugging all of this stuff in to figure out what these values were. But in this problem, in part B, you're actually solving for R. Okay. Where would I put the 200,000? Remember, this is my present value formula. And 200,000 is not the present value. It's the future value. So I would use this formula and plug 200,000 in for A. Okay. Questions? Any questions about that? So for part B, it would be like, it would look something like this. And then, of course, right, my rate, E to the rate. And what do we say about the time? The time is 18 years. So it looks something like that. And then you're solving for R. Okay, moving on. Number 21. This one's the same idea. It just looks different because it's not talking about money anymore. It's talking about national resources. Okay? National resources. Yeah. Is that what they're called? Natural resources. That's what I meant. Natural resources. In the year 2004, the world reserves of natural gas were approximately 9,671 trillion cubic feet. In that same year, the world consumption of natural gas was approximately 100.2 trillion cubic feet. And was growing exponentially at about 2.6% per year. Okay. Well, notice that right there gives me an exponential equation. Right? I can go ahead and model an exponential equation just based off what it's given me so far. And what is it modeling? Let's look. This models our consumption of natural gas. So I can actually model this consumption of natural gas as follows. My initial consumption is 100.2 trillion E, but this is growing at a rate of 2.6% each year. So this equation models my consumption rate. Wait a second, that means this is a rate function. It's a rate function. Okay, let's keep reading. If the demand continues to grow at this rate, and no new reserves of natural gas are found, in what year will the world reserves of this resource be depleted? Okay, how are we going to do this? Well, this is in chapter 5, so guess what we're going to use? We're going to use an integral. Why are we using an integral? Why are we using an integral? This goes back to the same idea that we talked about in this one. If you have a rate function, what will the integral tell you? Total change. So if I come to this problem right here, and this represents my consumption function, your rate of consumption, what will the integral give you? Total consumption. Right? My integral is going to give you my total consumption over a certain number of years. So what do we want to do here? How do we want to set this up? Based off of that, how do we want to set this up? How are we going to set this thing up? Well, I'm going to set up an equation in order to solve for something, right? What am I trying to solve for? I'm trying to solve for a t value, right? How long is it going to take for all of the natural gas to run out? The world reserves of natural gas to go to zero.
Just put not over K.
Because are you thinking like we're letting it happen indefinitely? What do I want my total consumption to be? 100%. Well, what's 100%? It tells you what the current reserves are. So what am I going to set this integral equal to? I'm going to set it equal to 9,671. Are we okay with that? Do we see why we would want to do that? Because we want to look at how many years it's going to take for my total consumption, my total change to end up equaling the current reserves. Okay. What are my bounds? What's my lower bound? Let's start with that one. What's my lower bound? 0. Yeah, my lower bound is just 0. Well, eventually I'm gonna consume. If I try infinity, this is a growth function, which means I'm gonna get an infinite value if I go all the way to infinity. I don't want to go all the way to infinity. I want to stop at some point. I want to stop once my consumption reaches 9,671. This means I don't actually know where to stop yet. This is the value that I'm going to be solving for. My upper bound is just going to be a variable. I'm going to use uppercase T. Uppercase T represents the specific point that I need to stop when I've now consumed all of the natural gas reserves. Okay. Any questions about how we set this up? It all boils down to the fact that the integral of a rate function gives you that total change. So how would I actually go about solving this? Do I know how to take this antiderivative?
Yeah.
Absolutely. That's an antiderivative we can handle. So I get 100.2 over 0.026 e to the 0.026t evaluated from 0 to capital T. What is 100.2 divided by 0.26? 100.2 divided by 0.026. Okay. I get 3,853.85. And then I still need to evaluate it at my bounds. What happens when I plug in capital T? Nothing. It just replaces my lowercase t, right? So I'm left with e to the 0.026 times capital T minus, what happens when I plug in my lower bound? What happens when I plug in 0? Right, I've already taken care of this term right here, 100.2 divided by 0.026. I've already taken care of that out here.
So it'll be 1.
Right. So if I'm just looking at e to this, if I plug in 0, I end up with 1. Right? Everybody okay with that? So that's what I'm left with. Now I can start solving for t. First, let's divide this. Okay. Let's see. 9671 divided by 3853.85. And I'm left with 2.509438, yada, 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 6. I'll stop there. E to the 0.026 capital T minus 1. What would I do next? Add 1 to both sides. I get 3.509438.6 equals e to the 0.026. What do I do next? Take the natural log. It's been a while since we've done this kind of stuff, right? Solving for a variable that's in an exponent. I have to take the natural log of both sides. And I'm left with t, capital T, equals natural log of 3.509438.6 divided by, let me erase this stuff. Divided by 0.026. And that's going to give you your time value. Questions about that? Questions about how we set this up? Okie doke. Let's move on. Number 22. Okay, 5.3. This is where we got into improper integrals. And so the example we're going to look at is find the accumulated present value of an investment if there is a perpetual continuous money flow. What does perpetual mean? What do I mean by perpetual? Perpetual continuous money flow? Yeah, it means I'm letting it go on forever, right? There's no set end time. And if I think about the accumulated present value formula, right? We wrote that down up here. If I think about this accumulated present value formula, what's going to happen if I let t get infinitely large?
Will it reach 0?
This term will go to 0. Right. This term will go to 0, and you're just left with r over little r times 1. And so that's where, if you guys remember, is if my money flow is perpetual, I end up with this really nice formula of your continuous income stream divided by your rate. And you're done. So that's all there is to number 22. Okay. 23. Aha! What type of problem is 23? Yeah, this is a differential equation. Right. How do I know? Because I've got an equation that's in terms of both x and y as well as dy over dx. It's in terms of the derivative as well. So what was my process for solving this again? Separate the variables. Right, it was this idea of separating the variables. And that includes the dy and the dx. So I'm going to move the dx over onto the right side. And then I need to divide both sides by y. I'm left with 1 over y dy equals 3x squared dx. Okay, I separated the variables. Now what? Now what?
The derivative of both sides.
Close. Not the derivative.
Antiderivative.
The antiderivative. Take the integral of both sides. Right. I'm going to take the integral of both sides. Integral of 1 over y dy, integral of 3x squared dx. Okay. What does that left side give me? What's the antiderivative of 1 over y? Natural log of y. Right. Very nice. So we get natural log of y equals... Oh, and do I need to worry about the plus c? Not on the left side. Just worry about the plus c on the right side. Antiderivative of 3x squared.
X cubed.
Yeah, just x cubed. And of course, like I said, we'll go ahead and worry about the plus c on this side. Uh-oh, I lost it. There we go. What's my final step here? Notice this one doesn't come with an initial value, so I don't have to worry about solving for c at all. There's no solving for c in this problem. So what's my final step?
Solve for y.
Solve for y. How? Y is inside of this natural log. How do I get rid of that natural log? I use an e function. The e and the natural log will cancel out, and I'm left with y is equal to, we'll go ahead and plug this one in and see if we get it right, e to the x cubed plus, where's my plus? Nope, that's not my plus. Plus, where are you, plus? Okay, ABC plus C. Notice how I have to keep that plus C up in the exponent. Okay, keep the plus C in the exponent. So let's try it. No. It's supposed to be. But we've talked about these before where if I wanted to simplify this, I'm just surprised that they're being sticklers about it. No, I don't think they need to capitalize the C. We have talked about how, though, I can use my exponent rules. I can use my exponent rules to split this up as, right, e to the x cubed times e to the c. That's one of my exponent rules. And what is e to an arbitrary constant? It just becomes an arbitrary constant. So let's see if it likes this better.
I think that's what it is. I remember doing that.
Yeah.
You have to take down the C and put it in front of the E.
Yeah, you can put it in front or behind. Since I don't want to have to worry about finding the multiplication button, I'll put it in front. And yeah, that'll work. So even though my answer was technically the same, they want it this way. Okay. Questions about that one?
Will we get it wrong on the exam? We put it the other way?
Obviously, yeah, which is not fun. So just be careful about that on the exam. Okay. Next question. Number 24. So we have now reached chapter 6 stuff. The last 5 questions are all chapter 6, which means we're dealing with multiple variables here in chapter with the rest of these problems. So 24 is just here's your multivariable function in terms of x, y, and z. Evaluate it at this point. What does... Oopsies. Zoom in. Zoom. What is 6 going to be? X, right? Plug that in for your X value. Negative 3, plug it in for your Y value. Positive 1, plug it in for your Z value. So, right? So in our case, in my case, right, f of 6, negative 3, 1 means I'm going to have 3 times 6 minus 8 times negative 3 squared plus 8 times 1 cubed minus 5, right? I'm plugging 6 in for X, negative 3 in for Y, and 1 in for Z. Questions on this one? Pretty straightforward. Pretty straightforward. 25. Domain. Domain of multivariable functions. Well, why is domain even something I'm worried about with this problem? What do I have in here that's going to affect my domain? Why do I need to worry about domain for this specific problem? Oh, man. I'm in another room here. What's affecting my domain? What's complicating my domain? The square root. So, if I just look at what's in, well, I guess what needs to be true for square roots? What's my rule for square roots? No negatives. That's my rule. So what does that mean? That means what I can do is I can pull out everything inside the square root. So negative 5 plus x squared minus y. I can just look at what's inside the square root and say, what? This has to be greater than or equal to 0. I cannot be negative. So where do I go from here?
See what one matches that.
Yeah, see which one matches that. And you'll notice all they've done is just solve for y. They've just solved for y. So if I solve for y, I get negative 5 plus x squared must be greater than or equal to y. Which one does that match? C. Careful. Careful. Even though the signs are facing the same way, I've switched where the y is. Because now the y is on the left side. So if I switch where the y is, I also have to switch the inequality. Good. Very nice. Woohoo! Okay. Partial derivatives. So if I zoom in on this, there's your function. F sub x, it's your partial derivative in terms of x. F sub y, partial in terms of y. What does this say? What is this telling you to do? Find that same partial derivative and then plug that value in. Right? Plug negative 4 in for x, plug 6 in for y. Okay. And let's just remind ourselves how these partial derivatives work. Here's my function, x square root of x squared plus y squared. If I wanted f sub x, what does that mean I'm doing? Taking the derivative in terms of x, what do I do with y? Treat it like a constant. Right. So how would I take this derivative? What is this going to require me to do or use? Chain rule. I need chain rule for this. Okay. So I'm going to take, right, this is the same thing as x squared plus y squared to the 1/2 power. So I'm going to use the chain rule here. I get 1/2 times x squared plus y squared to the negative 1/2. Right? I subtract 1 from the exponent. I get negative 1/2. But then I use chain rule. What's my derivative of the inside? And since I'm doing this in terms of x, right? Since this is f sub x, my derivative is just 2x. What happens to the y squared? It just goes to 0 because it doesn't depend on x at all. That term doesn't depend on x. So it goes to 0. Okay, very nice. Your 2's will cancel. Any questions about these partial derivatives? Any questions? Okay. Oopsies. 27. Okay, the last two are these last two are some good applied problems here. Okay. So this is the whole units of labor, units of capital type problem that we worked last week, that we looked at last week. Okay. Part A, all you're doing is just plugging in values for x and y. Okay. And then part B is finding the partial derivative. This one has multiple parts. Do we want to go through the whole thing? We did just kind of barely look at this one last week. But I guess we have time. So let's look at each part. It's equal to 5. It's not. No, I'm pretty sure it is. Oh, darn it, I got it wrong. So there you go. So part B is just finding your marginal derivative. Remember, these are the two different ways you could write it. P sub x or f sub x, or with these fancy d's, right? dp over dx, that just represents the partial in terms of x. So this is me taking the derivative of it, in terms of x. If I'm taking the derivative in terms of in terms of x, how do I treat that y? I treat it like a constant. So I should have 2200, right? I'm going to treat 2200 as a constant, right? So I'm just going to leave that there. I'm also going to have y to the 1/5. I'm not going to change that at all. Why doesn't this one go to 0? Oopsies. Back. Why doesn't this y term go to 0? Because it's multiplying, right? Because everything's being multiplied together. It's not two separate terms that are being added or subtracted. It's all one term. So instead, I'm going to just keep that y there when I take this derivative. Okay, now, there we go. Now when I take the derivative of my x term, I'm going to bring down the 4/5. And let's see, there we go. Nope, I do not want that. My parentheses. Nope, don't want that either. Okay, so I'll just do it this way, 4/5, and then x to the negative 1/5. Right, when I subtract 1 from the exponent, I get negative 1/5. 4/5 minus 1 is negative 1/5. Let's try it out. Nice work. Okay. Partial in terms of y is going to be very similar. But I'm going to skip past it. I'm pretty sure it's 5. It's not? No, it is. So then what does it ask next? Evaluate your marginal productivities at these values. What does that tell you to do? Same thing as like we just did in the last problem. That just means now that you have the now that you have the partial derivative, here's an x value to plug in, here's a y value to plug in. See what you get. Okay. Let's check our answer. I know 5's wrong. Oh well. I'll try 7 this time. But there's one more part to this. What do these marginal productivities actually mean? Okay. If I think about P sub x, my marginal in terms of x is labor, y is capital. What are we assuming about y if I'm taking my marginal in terms of x? We're assuming that it's staying constant. So, supposing that capital is fixed at this amount, right? It's staying constant at $14.99. Then a 1 unit change in labor will cause production to increase by about 3,753. So that's what it means. That's what these derivatives mean. Because they're derivatives, it's a rate of change. Increasing the labor by 1 increases your production by this much. Okay. Any questions about this problem? There's lots of stuff going on here. Any questions about this problem? Okay, last problem. I didn't actually write anything down for that one. So I'll just switch that to number 28. Okay, a company produces 2 types of solar panels per year. X thousand of type A and Y thousand of type B. Multivariable function, right? You've got 2 things that are independent of each other. Type A and type B solar panels. The revenue and cost equations are given as follows. So there's your revenue and there's your cost. Determine how many of each type of solar panel should be produced to maximize profit. So now we get into optimization. Okay. This was 6.3. How do we optimize a multivariable function? Well, first of all, I need my profit equation. Since I'm trying to maximize profit, I need my profit equation. Profit, of course, is just... this is a multivariable function, so it's not just in terms of x, it's also in terms of y. Your profit equation... Right, revenue minus cost. Okay, so in my case, I get 4x plus 5y minus x squared plus 3xy minus 8y squared minus 14x plus 79y plus 4. Why did I switch the signs for all of my cost ones? Because I'm subtracting, right? Because I'm subtracting, I switched all the signs for all of those, all of my terms in my cost equation. Okay, simplify this a little bit. Combine like terms. Negative x squared plus 3xy minus 8y squared minus 10x plus 84y plus 4. Okay, so there's my profit equation. How does optimization work with multivariable functions? How does optimization work? What do I need to do first? That's my first step. I need to find critical points. Right? That's how it works with one derivative or one variable. You have to find your critical values because your critical values are where your minimums or maximums can happen. How do I find critical points with partial or with multivariable functions? I take the partial derivatives, set both of them equal to 0. Right. I take my partials, set them both equal to derivative or both equal to 0. Okay. And clear some of this other stuff out. Oh boy, so let's do partial in terms of x. I get negative 2x plus 3y plus 0 minus 10 plus 0 plus 0. There's my partial in terms of x. Partial in terms of y. 0 plus 3x minus 16y plus 0. Plus 84, plus 0. Questions on those partials? Everyone okay with those partials? Okay. How come with my partial in terms of x, I was left with a y value? Once again, because this term has both x and y in it, for my partial in terms of x, I'm going to treat the y as a constant, which means it stays there. The 3 stays, the y stays, and then I just take the derivative of x. Derivative of x is just 1. So 3y times 1. Okay. Like we said earlier, I'm going to set both of these equal to 0. I'm going to set both of these equal to 0 and see what happens. Okay. Let's start with my top one. I get 3y minus 10 equals 2x divided by 2. You can solve for either variable. It does not matter. It does not matter which variable to solve for. I get 3/2 y minus 5 after I divide by 2. Okay. What do I do with that? Plug it into the other one. Right. I'm going to plug it into the other one. So I get 3 times 3/2 y minus 5 minus 16y plus 84. And what do I want to do with this partial derivative when it, once again, you guys have already told me. I want to set it equal to 0. Now this is all in terms of y, which means you can go ahead and solve for y, which will get you to your answer. Okay. Any questions? We made it to the end of this final review.
Do you have?
Yeah, go ahead.
On the last one, I believe, of Unit 6,
Okay.
there was, the last question of the last assignment is making a box.
Mm.
I do not.
Yeah, that's the box with the open top,
Yeah.
right? Yeah. Okay. Box with the open top. This is, the last question in that 6.3 homework assignment, right? So the idea behind this is, of course, the numbers are going to be slightly different depending on your problem. But if I remember right, it's like $5 per square foot for the base and $4 per square foot for the sides. And we want to minimize our cost. So let's just think about what my cost equation would look like. Okay. Well, a picture might help. So if I draw a picture of this, here's my length, here's my width, and here's my height. Okay. Well, how big is the base? Since it's $5 per square foot, how many square feet is the base? How would I actually calculate that? I don't know yet because I don't know the dimensions, but how would you calculate the area of the base? Width times length. If I'm thinking base, right? Width times length. So, it's W times L will give me my base, and it's $5 for every square foot. So I'm going to multiply that by 5. Okay? The sides are going to be similar. How do I get the area of this side? That's just height times width. And it's $4 for that side. So $4 times height times width. And then this front side. How do I get the area of that front side? Length times height. But it's $4 for that side. So I get this. 5 times length times width plus 4 times height times width plus 4 times length times height. But there's still something we're missing though, and that's the fact that what's the area of the backside? It's the same as the front side, which means I can just take this value and multiply it by 2. And same with this value. This side, the area of this side is going to be the exact same as the area of this side. So I can also multiply this one by 2. Okay, so this leaves me with the following equation. And this is the equation that I want to optimize. But the problem is I still have too many variables because this has 3 different variables that I'm worrying about. I don't want to have to worry about 3 different variables. How do I deal with that? It gives you a set volume. It says the box has to be a certain volume. Well, volume is just length times width times height. So whatever that fixed volume is, let's say your fixed volume is like 2,000. Okay. You can use that fixed volume to solve for one of your variables and then plug that into your cost equation. And then from there, you just take partial derivatives, set them equal to 0, and so on and so forth. Just like we did this past one. Okay. Best of luck in your future endeavors, everybody. Good luck with the test tomorrow. Starting tomorrow. You don't have to take it tomorrow, but starting tomorrow. Best of luck with that. And once again, reach out. Let me know if you have any questions about grades or anything. Since attendance is now, there's no more classes to attend, I will go ahead and adjust your attendance probably tomorrow so you guys can see what your attendance grade looks like.
Thank you.
Yep. Enjoy your summer.
Thank you.
Mm-hmm.